Hello and welcome to our notes on friction. Friction is actually one of the more complex forces that we're going to study this year. It's not complex in terms of what it does, but there's just a lot of different situations where friction actually does something that's fairly unusual or something that you wouldn't expect. Thankfully in Regents we stick to mostly the basic applications of friction that are fairly easy to understand. In AP Physics we talk a little bit more about the more advanced scenarios, but we don't even fully get into it then. What are the characteristics of friction? Let's just talk about, in general, what friction does. Okay? Friction is simply a force that acts, for our purposes, we'll just say against motion. Okay? It acts against motion. And it happens when you have an object or objects and they try to move either past or through one another. So it has to do with the relative motion between two objects. If one object tries to slide past another and it's in contact with the second object, there might be some friction. If you have, for instance, with like air resistance, if you have an object that's moving through air, that would also be a type of friction. Air resistance is just friction, but it's not with two objects, it's with an object moving through a fluid, like air. And then, kind of the most obvious one, for our purposes, for the most part, is that a lot of times, friction will cause objects to slow down. I guess that's not always true, but that's true for a lot of the cases that we're going to see. In some circumstances, I'm not saying in all circumstances, but in some circumstances, there's a formula to calculate the size of the force of friction. And that formula is right here under the Newton's second law equation. It is Ff for force of friction, right there, equals this funny looking U times Fn. Now remember, Fn is the normal force. Let's talk a little bit about what that mu is. Mu is or that funny looking letter. It's called a mu, mu, it's a Greek letter. It's all the way down here at the bottom, and that is known as the coefficient of friction. Okay? So you're going to get used to this equation. It's useful in some cases, not in all cases. Ff equals mu Fn. And again, the mu is known as the coefficient of friction. It has no units on it. What it does is it shows the relative strength of the force of friction. If you have a higher mu, if you look at the equation, it kind of makes sense. If mu is bigger, that tends to make the force of friction bigger. After looking at this equation a little bit, there's really two takeaways. The first is that Ff, the force of friction, depends on two surfaces involved. It depends on what objects are moving past or through what other objects, okay? And the reason that this is important is because mu, the coefficient of friction, is different for each pairing of surfaces. Okay? Think of two surfaces that have a lot of friction when you're trying to rub them over one another. Like, let's say if you had two pieces of sandpaper, really coarse sandpaper, there's a lot of friction involved if you try and slide one past the other. That would mean that mu is really high. It's a big number for those two surfaces. On the other hand, something that does not have a lot of friction on it, let's say like rubber on ice, like a hockey puck, that mu would be very small. And that would in turn change what the force of friction is. One of the misconceptions I see sometimes is people thinking mu stands for the force of friction. It does not. Mu stands for what is known as the coefficient of friction. The coefficient of friction is something that helps us to calculate the force of friction in certain circumstances. It is not the force of friction itself. Ff is the force of friction. Mu is the coefficient of friction. They are related. They are not the same thing. The other takeaway from this equation has to do with the normal force. The greater the normal force, the greater the force of friction. If Fn increases, then Ff increases. Now here's what this usually means. Usually, more massive objects have a higher normal force acting on them. So usually, they also have more friction acting on them. That's not always true, but it's mostly true for the circumstances that we're going to see this year. Okay? Bigger Fn, and we'll see why the normal force increases for more massive objects in a little bit. There's actually two different types of friction. There's both static friction and kinetic friction. Static friction is simply friction that acts on an object when it is at rest. In other words, the velocity is 0. Kinetic friction is friction that acts on an object in motion. It turns out that kinetic friction is actually the simpler of the two types of friction to talk about. Static friction can be a little bit more complicated. Let me show you why. Take a heavy stationary object, something with a lot of mass, and give it a small push, and it's not going to move. What force causes it to remain still? Well, if we think about it, if you got this object, and you give it a push, so let's say we have an applied force, then if that object is not going to accelerate, if it's going to remain at rest, there must be a force of friction on it. And what type of friction is it? That's got to be static friction. And how big is that force of static friction? Well, if F net x equals Fa minus Ff, I'm running out of room here, I shouldn't have written that there, equals max, there is no acceleration, therefore the applied force is equal to the force of friction. Okay? Given that it's not accelerating, it's at rest and it remains at rest, the applied force must be equal to the force of friction. The force of friction balances your applied force, that's why it doesn't accelerate. So what force keeps it in place? Static friction equal to your applied force. Okay? So again, that's kind of like, I have this very heavy water bottle right here. If I were to push on the water bottle a little bit like this, well, this is a kind of tippy water bottle, but if I were to push on it, okay, I'm exerting a force upwards. I wish it would stop wobbling. I'm exerting a force upwards from your perspective, and it's not moving. Okay? That means that the force of friction must be equal to my applied force that I'm exerting on this bottle. What happens if you push a little bit harder, but it remains still? Let me draw another free body diagram. Here's our object. I put a bigger applied force on it. But if it still is remaining at rest, what must have happened? In order for there to be no acceleration, the force of friction had to increase. There's still no acceleration, so the applied force must still be equal to the force of friction. But if I pushed harder, then my applied force increased. And if the applied force must still be equal to the force of friction, the force of friction, static friction, must have increased. So I'm pushing, and I'm pushing even harder. It's still, oh, I got it to move. And it's still not moving. That means that the force of friction acting on the object must have increased. So static friction must have increased to match the applied force. What I'm supposed to be showing you here is that the force of static friction on an object is not necessarily fixed. It's not one value. It increases to balance the applied force up until a certain point. Okay? Because obviously, if I have my water bottle here, there is some point at which my force does begin to accelerate the water bottle. Okay? This point where the force of static friction can no longer balance your applied force is known as the maximum force of static friction. At this point, static friction can no longer balance the applied force, so the object accelerates, and if it was at rest, it begins to move. And it was at rest if we're talking about static friction. It accelerates, and I'm going to write begins to move. And if it begins to move, now we have a different type of friction acting on it. There's no longer static friction acting on our block. There is now kinetic friction acting on our object. Static friction. There's now kinetic friction once the object starts to move. So this equation that we talked about up here, mu equals Fn. Oh my god, Ff equals mu Fn. I cannot read this morning. That equation does not work in all cases for static friction, okay? The whole point about this is mu is a fixed number that you can look up. Fn is a fixed number that you can calculate. If we're talking about the static force of static friction not being fixed, then this equation wouldn't work in every circumstance. This equation very specifically only tells you the maximum force of static friction. Okay? So you must use this only to calculate the maximum force of static friction, not to calculate any force of static friction, just the maximum. And usually there will be kind of like code words for when you're supposed to be finding the maximum force of static friction, such as, I'm trying to think of an example right now. Like what's the biggest possible force of friction before this object accelerates? Or you might be asked what's the smallest possible mu that this would happen? That's why static friction is a little bit more complex than kinetic friction. Thankfully, once an object is moving, we're going to model friction as kinetic friction always has the same value for a certain pairing of surfaces. So in that case, you can always use Ff equals mu Fn in order to find the force of friction. I'm going to direct your attention to the front of the reference tables now, where you will find a chart in the lower right-hand corner that says approximate coefficients of friction, right down here. Okay? The table is repeated right here. This table gives the coefficients of kinetic and static friction for very common situations. Notice it gives all the kinetic ones, and only gives some of the static ones. If you have a problem that does not tell you the coefficient of friction, and it's not what you're trying to solve for, it's not what you're looking for in the problem, you can find it here. Okay? So if it tells you, if it lists the surfaces that are sliding over each other, like it says we have a wood box on a wooden floor, or a copper object sliding over a steel table, or a lot of times they'll do tires on a road surface. So tires are made of rubber on either concrete or asphalt, dry or wet. Rubber on ice is for like hockey pucks, wax ski on snow, that's pretty self-explanatory. Things like that. If it tells you the materials, it's a good bet that you can look here and find a coefficient of friction. One thing that I want you to notice as you look at the coefficients of friction here is that the static coefficient, when there is one listed, is always greater than the coefficient of kinetic friction. And take a second, you can verify that for yourself. It's always greater. Let's think about what this means in context of our equation, our force of friction equation, Ff equals mu Fn. If mu is bigger, then the force of friction is bigger. So what does this mean? It means that there is more friction acting on an object at rest than there is on an object in motion. What it boils down to is it is harder to get an object to start moving than to keep it moving. Much harder to get an object to start moving than it is to keep it moving. In other words, Once an object starts moving, the force of friction on it actually decreases because the coefficient of friction changes from static to kinetic. And that change always comes with a decrease in the coefficient of friction when we move from static to kinetic. Now let me talk a little bit about why this is. Okay? Why does this happen? Even objects that seem very smooth on the microscopic level are not very smooth at all. They're very jagged. And what happens when an object is at rest on top of or next to another object is these jagged surfaces kind of lock together, okay? If you imagine, like, take your fingers and you kind of just like interweave them like this is what objects are like. And this is not a very good model. This is what objects are like when they are at rest next to each other, okay? They're kind of locked into one another. When an object starts to move past one another, it takes a lot of force to get these objects separated enough so that they're not really locked in like this, to separate them to, like, let's say this level. And once you have this, the objects can move past each other a little bit easier than they could if they were really locked into one another. That's why the force of static friction is greater, or that's why the coefficient of static friction is greater than the coefficient of kinetic friction, and that's also why the force of static friction is typically greater than the force of kinetic friction. We're going to move on to some examples. Let's see if we can finish this page up. Our first example is how much bigger is the force of friction on a stationary 75 kilogram skier than on a moving 75 kilogram skier. So we know we're going to be making at least two calculations here, one for stationary and one for moving. Now the way I would approach this is I would think to myself, okay, the stationary skier, is there a simple equation we can use to calculate the force of friction? And as it turns out, there is. Ff equals mu Fn. And I guess let's look for the maximum force of static friction. Okay, what's the biggest possible force of static friction that could act on the stationary skier? So in both cases, we're going to use Ff equals mu Fn. We can actually look up mu in both cases for stationary and moving. If it's a skier, then we're dealing with waxed ski on snow. The coefficient of static friction for waxed ski on snow is 0.14. Also, notice all these are very low numbers. They're typically lower than 1. That doesn't always have to be the case, but they're typically lower than 1. Force of friction on the stationary skier is 0.14. Coefficient of static friction. Coefficient of kinetic friction on the moving skier is 0.05, right from the table. Now, what's the normal force? Here's where this becomes a little bit more work intensive. You don't know what the normal force is. All you know is that the mass of the skier is 75 kilograms. That is not the same thing as the normal force. How do we calculate a normal force? Well, there's not a set equation for it. The normal force you have to calculate after drawing a free body diagram and writing a net force equation. So we actually have to do that. The nice thing is the normal force is going to be the same regardless if the skier is moving or not. So I'm going to draw my free body diagram quick. We have a skier. Here's my axis. Forces on the skier. Force of gravity going down. Let's say there's an applied force going forward. The skier's trying to move forward. There's a normal force pointing upwards, and there's that force of friction pointing backwards. My net force equations. F net x equals Fa minus Ff equals max. I'm not really concerned with that one, though. I'm just looking for the normal force because I want to complete this equation. F net y, and the reason I want to do that is I don't know how big the applied force on the skier is. It didn't tell me. But I don't need to know that because if I just find the Fn, the normal force, I'll be able to calculate the force of friction. F net y is Fn minus Fg equals may. Now, regardless of if I know the skier is accelerating in the x direction or not, I do know for a fact that the skier is not accelerating in the y direction. It doesn't say anything about that, okay? We don't know anything about any acceleration in the y direction for the skier. So, I'm going to cross that off and write 0. Therefore, the normal force must be equal to Fg, and we know that the equation for Fg, the force of gravity, I can substitute in mg. So I can calculate the normal force very easily by simply taking 75 kilograms and multiplying by 9.81 meters per second squared. 75 times 9.81, the normal force is 735.75 newtons. Now, that seems like a lot of work to find the normal force, but I challenge you, there's really no other way to do this question. 735.75 newtons times 0.14 is a little tiny bit over 103 newtons. 735.75 newtons times 0.05 is 36.79 newtons. The difference between them is approximately 66.21 newtons. Okay? So a big difference in the force of friction between something that's stationary and something that's moving. Number two, when driving a car, more friction is better because your tires will have a better grip on the road. Okay? And that's typically true. Sometimes we think of friction as a bad force. That's really not the case. We need friction in order to drive, in order to walk even. Okay? We need friction. And usually you actually want, if you're driving, more friction because it makes it easier to turn and to stop. So, more friction is generally better. Explain whether it would be better to drive on a dry road surface as opposed to a wet road surface in terms of the coefficient of friction. All you have to do is compare the coefficients of friction between dry and wet. You should always notice that the coefficients of friction are higher for dry road surfaces than wet road surfaces. So, here's what I would write. Since mu is higher for dry surfaces than wet surfaces, and FF equals mu Fn, it is better, you get more friction to drive on dry surfaces. And anyone who has their license or permit knows this, okay? Everyone knows that it's easier to drive on those surfaces. It's slippery. When it's wet, it's harder to drive. Which road surface is better to drive on, asphalt or concrete? Explain in terms of the coefficient of friction. Again, if we want more friction, since mu is higher for concrete compared to asphalt, it is, and I'm going to put this in quotes, better to drive on concrete. Oh, and let's throw in the equation. Since the force of friction equals mu Fn. It's important to put that in there so that we can see that a bigger mu would cause a bigger force of friction. Now, the reason I put it in quotes is we don't see road surfaces made of concrete that often. We see road surfaces made of asphalt. Now, I can think of two reasons this might be. Concrete is typically expensive. It's possibly more expensive to pave roads with concrete than it is with asphalt, so we use something that's not quite as grippy, but still pretty grippy. Also, the higher the force of friction, the easier it is to shred things like your tires and kind of break them down over time. And we don't want to replace tires all the time. So asphalt is not quite as rough, doesn't provide as much friction, but might be better for the wear and tear on the tires. That's the two reasons I can think of that we don't pave with concrete and we pave with asphalt. Last example for this video, if you're driving on a flat road surface to maximize the force of friction, would you rather have a heavy car or a lighter car? And let's explain. I'm going to go back up here to my free body diagram. Let's pretend that this was a free body diagram not for a skier, but for a car. We see that the normal force is equal to, ends up being equal to mg. Again, that's not always going to be the case, but it's the case in here. So here's what I'm going to say. Since the force of friction equals mu Fn, and Fn on a flat road surface is equal to Fg, which is equal to mg, then it stands to reason that I could plug in mg in place of Fn over here. Okay? All I'm doing is substituting equations into each other. The force of friction should be equal to mu times m times g. For cars on flat road surfaces. It is better to have a more massive or heavier car. Should probably move this up, sorry. And again, the reason for that is if we want a lot of friction, it's good to have a big normal force. Normal force in this scenario, not always, but in this scenario, is equal to the mass times the acceleration due to gravity. If you increase the mass, you increase the normal force, so you must be increasing the force of friction. That's it for this video. When we come back, we'll do some more examples. Bye.